Hello everyone, Chapter 4, Lesson Alpha, Fundamental Trigonometric Identities. Objectives for today's lesson are to learn the fundamental identities, some of which are new and others that we've seen versions of before, and then use these identities to simplify, verify, and factor trigonometric expressions. Now, just an FYI, as we go to the factoring portion, this is going to seem somewhat, how shall I say, pointless, but I promise you later on in further lessons, this skill comes out, and it seems pretty simple, but it will make sense later on why we will be doing it. So, without further ado, let's get started. All right, so let's look at a couple of identities. First of all, the reciprocal identities. These are review identities. We know these. The sine of u or theta or x is always equal to 1 over the cosecant, right? Those two are reciprocals. Likewise, the cosecant is equal to 1 over the sine. Same applies to cosine and secant. Those two are reciprocals of each other, as well as tangent and cotangent. Okay, just keep those in mind. Each of those may be important when it comes to simplifying an expression later on. A very important identity is actually the quotient identity. Many times this can get you out of a bind. This is new, but it's not really. At this point, what we knew in the unit circle was that the tangent of theta equaled y over x. And we had defined y as the sine of theta and cosine as x. So if tangent equals y over x, it would make sense that tangent in the unit circle would be sine over cosine. Likewise, cotangent, since it is the reciprocal of tangent, would be cosine over sine. That's where all of that comes from with regards to the unit circle. So why don't we take a minute here and look at a couple of examples. Simplify the following expressions completely. You guys, at first, you're not going to probably see all the tricks of the trade here, but what I would suggest to you is to just take it slow, and if you're in doubt, look back at your identities and see what you might be able to use to simplify the expressions. Okay, so there's not a whole lot I can do to simplify the sine of t. However, the cotangent of t is cosine of t over sine of t. And cosine, not a whole lot I can do there. Now, what could I do here? Well, a couple of things. I'm going to multiply these two expressions together. That would give me sine of t plus cosine squared t over sine t. Now, it doesn't seem that much simpler than it was before at the beginning of the problem. So what I'm going to do is I'm going to get a common denominator, which means I need a denominator of sine t, which requires me to multiply top and bottom over here of the first term by sine t. That way I'm technically multiplying by 1, sine over sine. So I will get sine squared t plus cosine squared t, and now I can combine these to be one term over sine t. Notice how the denominator and both are the same, so I can combine it to be one term. Okay, now I have, in this case, gotten a little ahead of myself, and you're going to see on the next slide what's called the Pythagorean identity, but the numerator here is equal to 1, and I won't explain yet, but a staple identity that you'll have to be aware of is that cosine squared plus sine squared, or the other way around, will be equal to 1. Okay, now I can simplify this and turn it into 1 over sine is equal to cosecant of t. So what I've just shown is that the expression above, by doing, how did I do that? By doing just a sequence of algebraic changes using identities, I've shown that that is equal to cosecant of t. Okay, let's look at the second example. Not much I can do with cosine of beta. Typically, you guys, angles are Greek letters are used to represent angles, but we can also use t or x as well. Tangent is equal to the sine over the cosine. And what's really nice is in this case we see that we get a reduction of the cosines. So cosine beta times tangent beta is equal to sine beta. That's as simple as we can make it. Outstanding. Okay, in the next one, cosecant is of course defined as 1 over sine, and cotangent is cosine over sine. All right, now a couple things you can do. If you see it and recognize it right away, the signs can reduce. Otherwise, 1 over sine divided by cosine over sine is the same as 1 over sine times tangent, or sine over cosine. So you'll see here, same thing, sines reduce. I get 1 over cosine, which is equal to the secant of x. So the original expression is equal to secant of x. It's a puzzle, guys, and it's a fun puzzle if you get into it. Don't get addicted, though. Well, maybe get addicted. That's a good addiction. All right, let's move on to the next identity. Okay, the next identities are the Pythagorean identities. Now, the Pythagorean identities come directly from this image that I've got drawn here, where u is the angle, the acute angle, x is the x-coordinate, y is the y-coordinate, and 1, of course, is the hypotenuse of the right triangle that's given. Now, in the last slide, what we did was we defined x as cosine of u, or cosine of theta. In this case, the angle is called u, and y is the sine of u. Therefore, Pythagorean theorem would tell me that sine squared plus cosine squared is equal to 1 squared. Now, that is one of the most used identities that you will see throughout chapter 4, as well as into calculus as well. So be aware of that. Now, there's two other forms that we could write this in. We could say that 1 minus cosine squared of u is equal to sine squared of u. All I did was subtract cosine squared from both sides here. Just subtracted it over, got 1 minus cosine squared is equal to sine squared. And the third form for this one would be that 1 minus sine squared is equal to cosine squared. So there's actually 9 Pythagorean identities. Here are the first 3 right here. Okay, so this is numbers 1 through 3. Okay, now let's take sine squared plus cosine squared is equal to 1, and let's divide everything by sine squared. Let's see what happens here. Okay, so sine squared divided by sine squared becomes 1. Cosine, oops, I'm going to have the wrong one here. Cosine squared divided by sine squared becomes cotangent, and 1 divided by sine squared becomes cosecant squared. So we get this identity over here. Okay, this is an equivalent identity, and it is also just as useful. I'm going to rearrange such that the other 3, or the other 2 forms of it come up as well. So you could get cosecant squared u minus 1 equals cotangent squared u, or cosecant squared u minus cotangent squared u is equal to 1. Those are identities 4 through 6. Okay, and you might have already guessed it, but if I divide everything by cosine squared instead of sine squared, I'm going to get this set of identities here. Sine squared over cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 over cosine squared is secant squared. And that's supposed to be a u. So if I rearrange again, I would get secant squared of u minus 1 equals tangent squared u, and secant squared u minus tangent squared u is equal to 1. And there are identities 7 through 9. Okay, so let's use them. All right, so example 2, simplify the following expressions completely. Let's work on the one over here. So first thing you can do is, what I notice is that I've got two terms. Okay, I've got this term right here, and I've got this term right here, and what they share is a sine of x. So I'm going to factor out a sine of x. That leaves cosine squared x minus 1. Okay, now let me rearrange that slightly, because I know that there is an identity, but it's 1 minus cosine squared x equals sine squared x. So this term right here and this term right here are closely related. What I'm going to do is I'm going to pull out a negative sign. And what that'll do for me is give me the following expression. Now I can do a replacement of this with sine squared x. So I get negative sine x times sine squared x. And when you take negative sine x times sine squared x, you get negative sine to the third. And that's it. We have fully simplified that. Okay, let's look at the next one. Okay, I like where we're starting here. I see this, and I know that 1 minus sine squared x is equal to cosine squared x. I don't know if I want to do anything with secant squared x yet, so what I'm going to do is I'm just going to rewrite. This will be secant squared x times cosine squared x. And of course, secant squared x is 1 over cosine squared x. If I multiply that by cosine squared x, I reduce the 2 and I get 1. That's a good one. There are other ways to do these, and there are probably, I'm not going to say I always do the most efficient method, but there are definitely worse ways to do these. Okay, so you can, like I said, it's a puzzle. You can work through it and do the long way and not realize it, or you can find the most efficient way on your first attempt. Some of it is luck at first, and then it becomes a skill as you become more familiar with the identities. All right, let's move on to the next identity. Okay, the next identity, from what I've found with pre-calc students along the way, is that it is the most enlightening of the identities. At first, it doesn't make sense. If you look at it in just a I want to memorize these identities type of mindset, but if you look specifically at a right triangle, I can teach you this very simply, and it's very straightforward. Okay, so I want you to look at, first of all, the triangle that I've given you here on the left side. Okay, in a right triangle, the three angles add to 180. If I know that this angle is 90, or pi over 2 radians, let's call it pi over 2. Oops, I zoomed out there. Let's call this pi over 2. Well, I know that pi over 2 plus theta plus the missing angle has to equal pi, 180 degrees. So I'm going to subtract pi over 2 minus pi over 2. That gives me that theta plus the unknown angle equals pi over 2. So the unknown angle is equal to pi over 2 minus theta. Okay, so now what I want you to do is just think logically. If you want to pause the video, you can. I want you to write in terms of A, B, or C the cosine of theta. Okay, you've paused the video, you've already done it. You would know that the cosine of theta is B over C, right? Adjacent over hypotenuse. Now what I want you to do is consider the sine of pi over 2 minus theta. Of course, pi over 2 minus theta is this angle right here, the other acute angle. What is sine of pi over 2 minus theta? You've now paused the video. You found that opposite over hypotenuse is B over C. Therefore, the cosine of theta is equal to the sine of the other acute angle in the triangle. That's all that these identities are saying. So I have confirmed this just by using right triangle trig. I'm not going to confirm the others. You could if you wanted to, but all of those match up and work. Those identities are very useful along the way. So let's look at an example here in example 3. Simplify the following expression completely. Okay, so before we go anywhere, let's talk about what this expression is actually telling us. This is telling us that the cosine of pi over 2 minus x times the cosine of pi over 2 minus x over cosine of x. Okay, well, we know, based on the identities given above, that cosine of pi over 2 minus x is equal to the sine of x. Right? The other acute angle is sine is equal to cosine of pi over 2 minus x. All right, so these are both, I should point that out, these are both equivalent to sine. So I have sine x times sine x over cosine x. Now what I'm going to do is I'm going to write this out as sine of x times sine x over cosine x. I'm allowed to do that only with multiplication, not with addition, subtraction. Okay, so this is equivalent to the sine x times the tangent of x. Right? This is a quotient identity right here, equivalent to tangent of x. And there you have it. I've simplified this completely. All right, let's keep moving to the next identity. Okay, even odd identities. I'm not going to do a whole lot with this other than maybe graph sine and cosine. But the following functions are odd. Okay, odd. Sine and cosecant, tangent and cotangent. Those are all odd. And even function or functions are cosine and secant. So let's quick draw sine. I'm going to draw a quick sine function. It's not perfect, but it'll be okay. You can see that there is origin symmetry, right? If I rotate any given point 180 degrees, this point becomes that one. There is origin symmetry. So sine, cosecant, tangent, and cotangent are all odd functions. So the following apply to it. Sine of negative u is equal to negative sine of u, whereas cosine and cosecant are even functions. So if I were to sketch cosine, not perfect, but it's okay, you can see that the inputs for positive x and negative x match up. Therefore, it has y-axis symmetry, making it an even function. Okay, so let's simplify the following expressions completely. Looks like we've got multiple identities in the second one. Okay, cotangent is an odd function. Therefore, I can rewrite cotangent of negative theta as negative cotangent of theta over cosecant of theta. Now from there, I'm going to rewrite them in terms of sine and cosine. Okay, so I'm going to use the quotient identities. So this will be negative cosine theta over sine theta. That's negative cotangent theta over cosecant, which is 1 over sine of theta. Just so we know, cosecant theta, 1 over sine theta. Cotangent theta, cosine over sine. And now we reduce. Now you're going to start to get used to reducing, or you can multiply by the reciprocal, and it looks like our answer comes out to be negative cosine theta. Perfect. Okay, the second example, first thing we need to do is use our cofunction identity from the previous page. Therefore, cosecant of pi over 2 minus theta is equal to the secant of theta. That's directly from the identities on the previous slide. Tangent is an odd function, therefore I could rewrite it as negative tangent theta. So tangent negative theta is equal to negative tangent theta. Secant is 1 over cosine theta. Tangent is negative sine theta over cosine theta. All right, again, cosines reduce. My answer, was almost done here, but I'd have negative 1 over sine theta. That's not complete. That would be negative cosecant of theta. That would be our answer, fully simplified. All right, let's keep moving. Okay, our next type of problem are problems where we verify that the equations are true using fundamental identities. Okay, now with that, you are not allowed to work on both sides at the same time. Okay, you can only pick one side to work on, and the side you actually want to pick is the more complicated side. It's much easier to simplify a complicated side than to expand a simple side. So I'm going to work on the first problem on this left side. I'm going to simplify this using the identities that I know. So sine theta, not much to change there. Cosecant would be 1 over sine theta. You can already see that I'm going to have some simplifying to do there. Sine squared, I'm not going to change. And the reason why, you could change it to 1 minus cosine squared. It's not going to be worth it for you. You're actually going to do less work by doing this. But if you go a more complicated route, it will get you to the same answer. It just might take you a little longer. So sine theta times 1 over sine theta is 1. And sine squared stays the same. And then by identity, 1 minus sine squared is equal to cosine squared theta. Therefore, we are complete. Okay? You could put a check mark, you could put a little initial, whatever you decide to do there. Okay, we have verified that the left side is equal to the right side by taking it along a sequence of identities and algebraic manipulation to show that it's true. Okay, number 2. This one I don't know if I left enough space for, but we'll see. All right, secant theta minus tangent theta times cosecant theta plus 1 equals cotangent theta. Clearly the left side is the more complicated of the two sides. I'm going to choose to work that left side, and in working that left side, I am going to FOIL. So let's multiply the two together. That would be secant theta times cosecant theta plus secant theta times 1 minus tangent theta times cosecant theta minus tangent theta. Now this looks like a total mess, but we're going to clean a lot of stuff up here real quick. Okay, what am I seeing here? Let's see. Let's see if we can multiply these two together. Okay, so secant theta is 1 over cosine theta. Cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. Tangent theta is sine theta over cosine theta times cosecant theta, which is 1 over sine theta. And tangent theta is sine theta over cosine theta. Oh boy, we want to come out with cotangent of theta. Let's see if there's anything we can do here to get us there. Okay, one thing you might notice right off the bat is that I've got in my middle term here, or one of my middle terms, I'm going to have sines reduce. And then you'll notice I'll be left with negative 1 over cosine. I get this negative 1 over cosine, which will reduce with 1 over cosine. So those two terms are going to go ahead and reduce out. So what I'm left with is 1 over sine theta cosine theta, which comes directly from this, minus sine theta over cosine theta. Now, in order to show that this is equal to cotangent of theta, I'm going to need a common denominator. So I'm going to multiply the second term by sine theta over sine theta, which gives me 1 minus sine squared theta over sine theta cosine theta. So we're getting close. Another identity that we can use is that the numerator here is equivalent, I'm going to work up here, is equivalent to cosine squared theta. That's over sine theta cosine theta. And cosine squared theta, one of the cosines there will reduce with the cosine here. And I'm left with cosine theta over sine theta, which is equal to cotangent of theta. One thing that I probably should have done, just so I didn't confuse you, is I should have left the equal sign on the right side so that we know I'm working the left side for the entirety of the problem, which is equal to our result that we're looking for. That's a good one, okay? Good use of multiple different identities. Let's look at the very last problem. The very last problem that I have here looks to be a somewhat challenging problem. I want to show that the following expression is equal to 2 cosecant theta. The first thing you're going to want to do is you're going to want to look at the denominators. And notice that the denominators are different here. Therefore, what I'm going to do to the first expression is multiply by the denominator of the second. Anytime you see this, you're going to want to get a common denominator. Okay? And then the second term, I'm going to multiply top and bottom by the denominator of the other term, sine theta. And I never, ever, ever expand the denominator, only the numerator. Okay, so I'm going to have something over sine theta times 1 plus cosine theta. It's very rare that I simplify the denominator. Okay, and then same thing here. Okay, so numerator. If I take 1 plus cosine times 1 plus cosine, I get 1 plus 2 cosine theta plus cosine squared theta. Okay, that's foiling the numerator on that left term. And the numerator on the other term, sine times sine, is sine squared theta. I'm liking what I'm seeing because I see a cosine squared plus sine squared, which is going to be 1. Okay, so I see this, cosine squared, sine squared, I see a 1. I also see another 1 here. So cosine squared plus sine squared is 1, plus another 1 will be 2, plus 2 cosine theta over sine theta, 1 plus cosine theta. Now you might already see it, but I'm going to factor a 2 out of the numerator and something nice is going to happen. You can see that that factor in the denominator is going to reduce. Okay, so watch this magical deliciousness here. This is awesome. Those will reduce out. I get 2, I think I just said deliciousness, which is kind of disturbing. I don't think I've ever used that expression. Looky there, I get 2 cosecant theta, which is exactly what I'm looking for. Guys, again, practice is going to make you better at this. Asking questions, making sure you're paying attention to these videos, as well as getting some work in. So let's go to the last slide for today. Okay, as I mentioned earlier, this factoring skill is kind of like, okay, why and how does this fit in? We're going to use it later on, so just kind of get used to it, okay? So as I look at number 1, if I asked you to factor x squared minus 1, you would say x plus 1, x minus 1, and you'd be correct. If I ask you to factor secant squared minus 1, it's very similar. It's a difference of 2 perfect squares. So I'd have secant theta plus 1 and secant theta minus 1. Outstanding. Okay, what if I asked you to factor 4x squared plus x minus 3? Well, I'm going to guess and check here, but I'm going to say, how about we go 4x and x, and we go with a plus 1 and a minus 3. Nope, that's going to be wrong. How about a minus 1 and a plus 3? I think that's going to be wrong too. How about a plus 1 and a minus 3? Yay, I like that. Okay, so you can see it's not like factoring is always easy for math teachers. I got some issues with it too. There we go. Okay, so if I factor 4 tangent squared plus tangent theta minus 3, very similarly, I would get 4 tangent of theta minus 3 and tangent of theta plus 1. Notice that I'm just doing the substitution. Let x equal tan theta in that one. Or over here, let x equal secant theta. That's all we're doing. We're doing a substitution and then factoring. And in this case, I can't really reduce much, so I'm good there. Okay, here's a problem, number 3. I've got two different functions, cosecant and cotangent. So that is an issue. However, I do have an identity that ties the two of them together. I believe 1 plus cotangent squared theta is equal to cosecant squared theta. Oops, theta. Cool. Okay, so cosecant squared is actually equal to 1 plus cotangent squared. So I'm going to substitute in here for cosecant squared a 1 plus cotangent squared. Make sure you have the right variable, x minus cotangent x minus 3. Okay, I'm going to combine the 1 and the negative 3. So cotangent squared x minus cotangent x minus 2. Now let's factor that. Okay, so let's equate that. Let's let x equal cotangent of x for a moment. If we had x squared minus x plus 2, we would factor that in this fashion. I suggest doing it this way. How about a minus 2 and a plus 1? Would that work? No, it would not. How about a... Whoops, I have something wrong here. I rewrote it wrong. That should be a minus 2. That's why it jacked me up. Okay, so a minus 2 and a plus 1. I like that. Let's equate that back to the original here. So if I factored that, I would get cotangent of x minus a 2 times cotangent of x plus a 1. In factored form, we would be good. And that is fully simplified. Let's get to a problem where I might be able to do some more simplifying. Okay, very similar to the first one. X squared minus 4 would be x plus 2x minus 2. Therefore, cosine squared x minus 4 would be cosine of x minus 2, cosine of x plus 2. Okay, I'm not going to change anything in the denominator. That's cosine of x minus 2. And we're going to get a reduction. So this would be simplifying, which would come out to be cosine of x plus 2. There you have it, guys. That is Chapter 4, Lesson Alpha on the fundamental trigonometric identities. Have a great day. Shoot me some questions if you got them.